Okay, so now we are looking at things not at a very detailed level. We are looking at depth averaged equations, and so let me just briefly review what we have been talking about. So this depth averaged equations you can think of, in fluid mechanics, you would have done macroscopic balances. So this is something like that we are doing macroscopic balances. We are not interested in the velocity at every point, but we are averaging over the depth so that we get a mean velocity and thickness and so forth. So in a sense, the equations have been, since they averaged, you're not interested in the spatial variation of the velocity at every point, but only the mean velocity in the layer. So this is the sort of problem we are looking at. So we have a thin or a shallow layer that is flowing, but what is unique here is that these particles are flowing on a fixed bed of the same material. And so as they flow, some of the particles could deposit on this bed. So the bed will rise wherever they deposit. And if the flow is very fast, then it could actually erode out. Then the height of the bed will decrease as the particles are eroded away. And we made a number of assumptions to come up with the equations to describe in a macroscopic sense the flow in this layer. First of all, we said any of these curvatures are negligible, so we'll just look at xy coordinates. We can just straighten out this whole thing and then it's fine. And then we assume that we're not very concerned about the exact profile in there, but we'll assume it to be linear, which is gamma dot times y. And that gamma dot can be written as 2 times u divided by delta, where of course, if you integrate Vx from 0 to delta and divide by delta, you will get u. So u is the mean velocity and delta is the layer thickness. So those are the two important variables. As the layer flows, we want to know what is the mean velocity in the layer in the x direction and what is the thickness of the layer. Now we also took into account wall friction, so that walls are perpendicular, so they are vertical walls confining this flowing layer on two sides. And when we do that, then we have to take into account this wall friction. We assume that the normal stresses in all the three directions x, y, z are equal and they're equal to the pressure. And then we have two regions of flow. One is the flowing layer, and we say that the shear stress is given by this in the flowing layer. And so here this is made up of a collisional part, like how Bagnor said. So that's why there's gamma dot squared. And then there's a frictional part, and this is the coefficient of friction. And of course, this free factor is nothing but the pressure. So it's the pressure times the coefficient of friction will give you the shear stress, or sigma is equal to mu into P. But when you go into the bed, the shear rate is 0. So then you'll have just the normal stress times the coefficient of friction. But this one will be a little higher than this because at the interface they have to both match. So mu m and mu s are the two coefficients of friction. One is for the flowing layer and one is for the fixed bed. Now if you plug all of this into the linear momentum balance and the continuity equation, then you will get these two equations, and we derived these last time. And this says that the rate of change of the layer thickness with time depends on the rate of change of the flux, that is u times delta is the flux, and gamma is the rate of deposition, the rate at which material is put in. I don't know if I derived this one, but we'll check that. And then the momentum balance equation is simply given by this. Del by del t of q delta is equal to 4 by 3 u squared delta by dx. Then this is the earth pressure term that comes from del sigma xx by del x. And then this g is delta sine beta. This is the gravity force acting. And this is the resistance due to the friction at the base. And this is the resistance due to friction due to the walls. So this is the equation. So the acceleration is essentially due to some other driving force plus the gravity minus the friction. And then of course, if we have continuity at the interface, that is if you put these two stresses are equal, and then we simplify, you'll see many things cancel out. And then you're just left with this equation, that mu m cos beta is equal to mu s cos beta times this. And so from this, if we simplify, we can easily get the shear rate as just g cos beta into mu m minus mu s by cd. Here d is the particle diameter, c is a constant. So in this way we have, essentially if we just look at this and this equation, then we have two equations and two unknowns. And then when we look at the continuity equation, then we'll have three equations and three unknowns. And the unknowns are essentially u delta and gamma. That's it. Those are the three unknowns, and then you have three equations. So we can essentially solve this. And so I'm going to look at today, I'll continue with this, and then we'll look at some of the simplifications. What happens if the shear rate is a constant? This happens in some cases. We look at the kinematics, that is, how does the, let's say if your flow is on a heap, then how does the heap shape change with time? Can we describe that? And then we'll do some simple examples. So today we'll probably not reach the examples, but we'll start looking at them. Okay. So any questions on this so far? No? Okay, so then let's go back to the whiteboard, as they say. So we were doing all this last time, and we did of the whole derivation, and we got this equation as I just discussed. And in what follows, I'm going to drop this term. The earth pressure term we'll neglect because d delta by dx is quite small. So that's why you get a much simpler equation. And then we saw that the continuity equation is there. And this is the rate of deposition, that is minus Vy at 0. So just go back to the original graph. So if you see this, Vy is the velocity in the y direction. So if you say Vy is positive, then the velocity particles are moving upward. But if you want to see what is the deposition at y equal to 0, that means that is minus of Vy at y equal to 0. So that is the rate of deposition. And that's why we have put gamma, that is the rate of deposition, as minus Vy. So these are the equations. And now let's go forward. And I want to just rewrite this equation again. But of course, as usual, I'll first write down what is today's date. We already reached 12th of October. And today is lecture number 30. So I'm going to I want to essentially simplify these equations out. Okay. So I want to write down this equation again. And so if we write the continuity equation again, so it is delta by del t plus del of u delta by del x is equal to minus of gamma. So this is one equation. And the second equation is u squared delta is just equal to g delta into sine of beta minus mu m cos of beta minus 2. Is there a factor of 2 missing somewhere here? No, this is correct. So then you just get mu cos beta mu w cos beta into delta by b. B, just to remind you now, all these terms are known to us, but if we imagine that the flow is happening between parallel plates like this, then this gap is just equal to B. So that is the gap between the plates, and the wall friction is mu W. So this is that term that comes. If we neglect wall friction, then of course this term will go to 0. So now this is what we want to start with. So the first thing is, let's look at a simplification which is assume gamma dot is just a constant. That is, it doesn't depend on space or time. And this is often seen in some cases. In some of the flows, this may be a good approximation. So supposing we do that, then the simplification that happens is that you can essentially relate u and delta in an easy way, because gamma dot, we have seen before, is just 2 times the mean velocity divided by the layer thickness. 2 times u is just the maximum velocity, so that is the velocity at the free surface, and when you divide by delta, that will give you the delta u by delta x, which is. So what we can do is, using this, we can substitute for u as just equal to gamma dot into delta by 2. So the mean velocity is given by this. And so wherever u comes, we can replace it by gamma dot delta by 2. So then the continuity equation becomes del delta by t plus del by del x of, now here I can just replace this u by gamma dot into delta. So that just gives me gamma dot delta squared by 2 is equal to minus gamma. And then if you look at the momentum balance equation, of course this is the momentum balance in the flow direction, then you get del by del t of, now instead of u we are going to put gamma delta by 2. So then again we get gamma dot delta squared by 2 plus 4 by 3 del by del x of, now here I'll have to put in gamma dot squared delta squared by 4. So you get gamma dot squared delta cube by 4 over here. And this is just equal to, and I'm going to put this as it is for the time being. I'm going to call this whole thing, just for simplicity, I'm going to call this as just A. So that I'm not, I'll substitute for it later. I'll put A back in there. Okay? Because just now I want to mainly work on the left hand side. So this implies, now if I simplify this out, gamma dot is a constant, so I can just pull it out of the brackets, and then when I take a derivative, I will get, so this is gamma dot by 2, and then I have to take del by del t of delta squared, so that gives me 2 delta into d delta by dt. Now here 4 and 4 cancels out, and again gamma dot comes out, so this will be plus gamma dot squared by 3, and then when I take the derivative I will get 3 delta squared into del of delta by del x is equal to A. So now here, if you see this, you know, again, you can see that 2 cancels out here, 3 cancels out here, and so you are essentially left with so this equation becomes gamma dot delta into del of delta by del t plus, over here you will be left with gamma dot delta into del d delta by del x is equal to A. So the momentum balance becomes this, where A is given by that all those terms above, so that is fine. And actually I should have simplified the continuity equation also, and if I just do it in the same way, I'll get del by del t plus, now here when I take this out, I'll get plus gamma dot delta into d of delta by del x is equal to minus gamma. So it's exactly the same way I did for the momentum balance. You can simplify it out. And so this, because gamma dot is constant, we can take it out. Now what is interesting is that this term inside the bracket is just equal to this. So now I can substitute that for minus gamma. So I'll get minus of gamma into gamma dot delta is equal to A. Now what is A? A is all this stuff. It is G delta into sine beta minus, you can see over here, mu m cos beta minus mu w also into cos beta times delta by b. So this is the what you get. And you can see over here that essentially delta cancels out on both sides. And what we have ended up with now, by making this simplification and then combining the two equations, we are getting that gamma is just equal to minus of G by gamma dot into sine of beta minus mu m cos beta minus mu w cos of beta into delta by b. This is what you get. So by doing, just some simple physics, we can get an expression for the deposition rate. And we would like to now compare this. You remember long back, 2 lectures back, I started off this whole discussion by saying that there have been some theories that have been just put down, which describe, they don't go into all the other details, but they essentially tell us that the deposition rate is given by some formula. And so, if I go all the way back to 2 lectures ago, when I just started talking, I started talking about all this and all this erosion and deposition. But then I also told you, okay, here is a expression for the deposition rate. Here's another expression for the deposition rate. Our expression looks very, very different. There it is just theta n minus theta. So now here, what is the way we can simplify this? Well, in certain cases, it's going to reduce to something that looks very much like that one. And the way that we'll do it is we can put, let's say that mu m is equal to tan of some angle beta m, because coefficient of friction, we can always write this tan of some angle. And this is just equal to sine of beta m divided by cos of beta m. Now if you substitute in there, then you will see that gamma is equal to minus G by gamma dot into sine of beta minus sine of beta m cos of beta divided by cos of beta m. I'm going to keep this as 1, and then I'll have plus mu w G by gamma dot cos of beta into delta by b. So I'm keeping that one separate. Okay. Now if you see this term, I can take cos of beta m common. So this is minus G by gamma dot. And then at the bottom, I will have cos of beta m. And then on the top, I will have sine of beta cos of beta m minus sine of beta m minus into minus cos of beta sine of beta. And then the second term remains the same, g by gamma dot mu w cos of beta into delta by b. Now, if you remember your trigonometry from your school days, then you know that this is sine beta cos sine A cos B minus cos A sine B. What is that equal to? Does anyone remember? I want someone to answer.
Sin A minus B.
Great. Just like to hear someone's voice once in a while. Thank you. So this is just sine of A minus B. A is sine beta and A is beta and B is beta m. So this is beta minus beta m divided by cos of beta m plus g by gamma dot mu w delta by b cos of beta. So here, this is the expression that we get. And you can see now it's looking a little like what the BCRE and other models were. Now, if we further suppose, of course, always beta and beta m are not very different. So we can always replace sine of beta m. So if we make some approximations, further approximations, in which we say sine of beta minus beta m is approximately equal to beta minus beta m because the difference is always small. And further, if we assume that the angles are close to 0 or the angles are small, and then if we assume that cos beta m, so there will be 1, maybe 0.9, 0.8, something like that, but it will be close to 1. So in that case, you will see that we get gamma is equal to minus g by gamma dot into beta minus beta m plus g by gamma dot mu w delta by b. And so if we say that further, if mu w is almost equal to 0, so that this term, the frictional resistance is very small, then we finally get that gamma is equal to minus g by gamma dot into beta minus beta m. And so the deposition rate just reduces to something like the models that I told you about. But the key thing is that here this deposition rate doesn't depend on the thickness of the layer. It only depends on G and gamma dot. So that means this is closer to the BRDG model. So what are the assumptions to go from the general model to here? The assumptions that we made is gamma dot is constant. That is one assumption. And then we also said that mu w is almost equal to 0, so there is no wall friction. And then we said that the angles are small. So these are the assumptions that we made to reduce our general model. And when we make these assumptions, the deposition rate is essentially given by the BRDG model. And in there, the BRDG model puts this as just some velocity v, and here we have got an expression for that velocity, and that is v divided by the shear rate, g divided by the shear rate. And you can see this as units of velocity. This is units of centimeters per second squared, and this has units of 1 by second. So when you divide the two, you will get centimeters per second. So that's the velocity unit. Okay. So this is something that just as a first step to say that okay, all this we are doing, it does make sense, and we can really try and use this model now to look at specific problems. And in fact, it's always nice to see if a particular theory reduces to some earlier theories which have been validated. So we saw how the both the kinetic theory as well as the JFP theory or the MUI model, how they reduced to the Bagnol theory, which was the earlier one. And here also we show how this model reduces to the BCRE model or the BRDG model, which is the earlier result. Okay, so now we need to do one more thing. So we know we'll be able to calculate what is the velocity in the layer. We know how to calculate the layer thickness, and we know how to calculate the deposition rate. So we know U, delta, and gamma. But usually what will happen is that we'll be able to calculate that at any instant. But if there's any deposition or if there's any erosion because of the flow, then obviously the shape of the heap will change. So we do need to look at the kinematics. So what does it mean? Kinematics means how will the shape of the heap change? So let's suppose we have this as our coordinate system. Now we'll call these two coordinates as H and W. And then our layer is over here. And this one is Y and X. And let's suppose that we are measuring this height as H, and that depends on W. Okay, so the height of the interface from the base is equal to this. So as things deposit, what you will find is that, since the velocity Vy is in the Y direction, so things are, there is a deposit in this direction, but the height is changing in this way. So if you want to find out what is the rate of change of height, then you'll see that del H by del T is equal to gamma, because if gamma is positive, that means it's depositing, so height will increase, so del H by del T will be positive, but you have to put in the factor of cos beta, because the velocity is normal to the surface and we want to find out the velocity in the vertical direction, so that is going to be gamma cos beta. So if beta is 0, then of course dH by dt is gamma. So if you're starting with a flat interface, that is x is coinciding with w, then you will get del h by del t is equal to gamma. But if beta is some small angle, then you have to multiply that by a factor. And then based on the geometry, we can just say that you can relate del h by del x, and that is going to be equal to minus of sine of beta and del h by del y is just equal to cos of. So we can do it the other way around also. We can also do del x by del h and you'll get some factor, but this is it. So now we have three more equations, and we have actually, three unknowns. Okay, we can see we now need to solve. So the unknowns now are u, delta, and gamma, which we had before. But then we also have h and beta. And so now we have five unknowns, and then we have five, essentially five equations, or we have six equations. So we have five unknowns, and it says here sufficient equations, because it essentially tells us the rate of change everywhere. I'm writing sufficient equations to solve. So how, when we first look at, once we start solving some problems, then we'll be able to get some ideas about it. So I'm going to start with the simplest possible problem where there is, the kinematics are not even involved, but that will help us a little bit to start seeing how to apply these equations. So supposing we have steady flow with frictional sidewalls. So we have done this type of problem before. We applied the mu I model to this, and we got quite a complicated equation. Now we are just going to look at the simplest possible case. And so here you imagine that we have this system, okay, and let's suppose that this is a wall here, so nothing can go out from here. This is a wall here, and let's suppose that we have a wall here. Of course, the plates are like this, and these are the walls. And then let's say we start pouring material at one end, then slowly the heap will form, and then at long times your heap will look something like this, and the material will slowly fall out from it. So at steady state, you will have an interface and you will have a surface, and this thickness is delta. Okay, so this is the system. Let's assume at steady state. Here you have a fixed bed, and this is the layer which is flowing. So at steady state, everything, there's no change in geometry. So you have a fixed geometry. So H is not changing with time. Okay. But we can get that from the other thing also. So let's just see. First, let's write down the continuity equation. If we write the continuity equation, we remember that d delta plus del by del x of u delta is equal to minus of gamma. Now, if we assume that, of course, it's steady state, so this is 0. And if we assume that both u and delta, since at steady state the flux must be constant at every point, just because whatever material comes in must go through at every point. So at steady state, because u multiplied by the thickness, so u is the mean velocity times the thickness, so this is the flow rate. The flow rate per unit width in the z direction, that has to be a constant with x. So this term also is 0. So at steady state, you will have essentially gamma is equal to 0. So this is the first result that we get, that in this problem, gamma is 0. Then if we write down the momentum balance equation, we have del by del t of u delta plus 4 by 3 del by del x of u squared delta is equal to, now I'm going to write, I'm going to combine the gravity and just like what we did just now, instead of writing it as sine of beta minus cos beta m, I'm going to write it as sine of beta minus beta m divided by cos of beta m. This is what we had just done up. And then this is minus mu w g delta squared by b into cos beta. So this is what you get. So this is your momentum balance equation, but now everything is 0. So essentially you have steady state, so this is 0. U delta is not changing with time, and so you expect delta is also not changing with time. So this is 0. So you're just left with this simple expression. And if we sort of cut out all the common factors, so g delta is common, so this gets cut out with this. So then we are just left with this equation, just gives us 0 is equal to sine of beta minus beta m minus mu w into delta by b into cos of beta into cos of beta m. And now if we sort of say, okay, look at small beta and the angle to be sort of small, then what you will get. So first of all, I'd like to say this, that if the walls are frictionless, then mu W is equal to 0 and beta is equal to beta m. So essentially in this steady state, the surface angle that you get is just equal to the neutral angle, beta m. So this is if there was no wall friction. But when there is wall friction, and then if we assume angle difference is small, then and of course mu w not equal to 0. In this case, you are left with beta is equal to beta m plus mu w delta by b into cos of beta into cos of beta. So what it actually tells you is that your angle of this interface, this angle is beta, as we have seen before. That angle will always be larger than the neutral angle. This is the neutral angle. If of course if mu w is 0, then beta is equal to beta m. But if mu w is something positive, there is some wall friction, then you will have this. And what it turns out is that this angle will increase as the layer thickness, as the thickness of the layer goes on increasing, this angle will increase. Okay, and this is of course this has been found experimentally also. And the final thing that we have is that if you want to find out what will be the layer thickness, then we know that your layer thickness, or let's say for example if we do overall mass balance, let's suppose that the material that is being fed at a constant mass flow rate m dot, then m dot is just equal to the bulk density times the mean velocity into b. B is the width. So this is going to be the mass flow rate in the layer. And now if we write down U is equal to gamma dot delta by 2, then you can clearly see that, I'm sorry, this is U delta into B. This has made a mistake. So this is U times delta into B. So velocity into the cross-sectional area is delta times B times the density. So this part is the volumetric flow rate times the bulk density will give you the mass flow rate. And then further you have U is equal to gamma dot delta by 2. So this gives us that the mass flow rate is simply given by rho bulk into gamma dot delta squared B by 2, or you can say that delta is equal to 2 into the mass flow rate divided by rho B gamma dot into B. So if we know what is the shear rate, then we can easily get the layer thickness. And from an earlier this thing, we have already seen that gamma dot, in the earlier lecture, we have already seen that this is related to the coefficients of friction mu m and mu s, and the other parameter of the model C. So this is also known. So now in this way we can solve for the entire problem. And I'll show you a presentation later that the experiments in fact do show that this is correct. So I'm going to just write over here all these things are validated by experimental studies. Okay, so in fact this simple model is able to predict experimental results quite well. The next problem that I will look at, and I'm going to just introduce it here and then stop. And that's another example. So that is flow on a heap with frictional side walls and a closed exit. So in the earlier heap, whatever material was coming in was allowed to just flow out. So here material is coming in here and then just flowing out. But what we can look at another system, same thing, that we look at this is a container, but now supposing the walls are right to the top. So I have essentially a system like this. As before, that we are looking from one side, but if you look at the 3D view, it is actually two plates like this, which are separated by a distance b, and we are looking from this side, and let's say this is the closed system, so there is no place for the particles to go. And as before, I'm going to put in a constant mass flow rate of particles from one edge. So what will happen is that the particles will again form a heap. So it will form a heap like this. But now it will not be a steady system, but what we will find is that in fact there is a flowing layer and then there is a continuous deposition. That there are particles being deposited at all points because there's nowhere to go, so the particles have to deposit, and what you'll find is that the material surface rises at a constant rate, and that rate depends on what is the rate at which you are feeding it. So this is the system that we want to analyze, and in the next class I'll do the analysis of this. And what we'll assume, of course, is it's a quasi-steady state, just to make things easier. That is, we'll not look at any time derivatives, and then we'll see how will this system sort of, how can we solve for this. Okay, so we will just take the continuity equation and the momentum balance equation at steady state and then try and see how we can actually get a solution, how we can get this, what is the flow velocity in the layer, what is the rate of deposition, and so all those things really. I should just mention that one person who is an expert in all this is Niladri. In fact, his PhD work relates to now some of the things that we are talking about. He's also looking at flow on top of a heap and all these things, including doing some experiments. So if you come to our lab, you can see his setup. Okay, so with that, I'll stop and I'll see you now on Thursday. Okay, so thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Bye bye. So, Neil, I was just thinking maybe we can discuss, but a lot of these things that I'm talking about these days could be, you can try and see if any of your simulation results also match.